Okay, so this is going to be some problem solving for chapter 9, just to look at it. And so these problems, actually, I got them from your homework, right? So yours might be similar or it might be this exact problem. Who knows? It all depends on what version you get. And so let's try to first start off with identifying our Lewis structures, right? So when you're looking at Lewis structures, you want to think about how many valence electrons do you have. So if we're thinking about valence electrons, and then for beryllium, we look on the periodic table, it's in group 2A, so it has 2 valence electrons. Calcium also has 2, potassium has 1, and gallium has 1, 2, and 3. Now, the reason why we know gallium is 3 is if we look at its electron configuration, that's going to be argon, 4s2, 3d10, 4p1. And so our valence electrons are not going to include the 3d orbitals. And that's because 3d is not the highest energy state. And so we're not going to include that as our valence electrons. Now I'm going to go ahead and zoom in here a little bit. Should make that a little bit easier for us to see. There we go. And so if beryllium has 2 electrons, remember that our Lewis structure, we can have no more than 2 electrons to each side, and no side gets to pair up before every side gets 1. So for beryllium, we're looking at a Lewis structure of Be2. Calcium, similar. Potassium has 1. And our gallium, we are looking for this one down here and not this one. Even though both of them have 3 valence electrons, we want each side to have 1 valence electron before we double them up. All right. Let's jump to our next one. So our next topic is going to be looking at our bonds. And so we're trying to look at this bond between calcium and fluorine, or silicon and silicon. And we're trying to identify whether they're going to be ionic or covalent. And so what we need to do when it's asking us this question is we need to pull out our electron negativity periodic table. And the reason why is because when it's asking for this, we need to know what the values are. So the way that we can tell the difference between ionic and polar covalent and covalent is all depending on our type of bond, which all depends on electronegativity difference. And so we need to pull up that chart first. All right, so I've pulled up my electronegativity chart here, and so I'm going to look at those differences. So for that first one, we're looking at the silicon-silicon bond, right? So silicon has an electronegativity of 1.8, and so we're really looking at a bond between a 1.8 and a 1.8. So when we subtract that, our electronegativity difference is 0, which in some ways we should already know, because if it's the same element, they're not going to have a difference in their electronegativities. And since there's no change in it, then it is going to be a covalent bond. And because it's such a small difference, then we know it's what we call a non-polar covalent. So we can classify it just as a covalent bond. And so remember, our cutoffs for our non-polar is 0.4. That's the same as the difference between carbon and hydrogen. A polar is going to be anything between 0.4 and our 2.0. Now, sometimes you see them use 1.7 as a cutoff for our ionic bond. Our book says 2.0, so that's what we'll use, but really we're looking at that range. So once we get up to that 1.5, 1.6, 1.7, 1.8, we're becoming more and more polar, almost to the point where we become ionic. And so the difference between your ionic character between 2.0 and 1.7 is not that much, right? It's just increasing and increasing at that point. So ionic is anything that's greater than 2.0 for those electronegativity differences. So looking at calcium and fluoride, well, calcium here is going to be 1.0, fluorine is going to be 4.0. So 4.0 minus 1.0, that gives us a difference of 3.0. So that's definitely an ionic bond. Between silicon and chlorine, well, silicon is going to be our 1.8. Chlorine is going to be 3.0. So 3.0 minus 1.8 gives us a difference of 1.2, which is not enough to make it ionic, but it is enough to make it polar. So there is an imbalance there. So that's going to be our difference there. Now, I saved H plus and hydroxide for last because it's kind of a more tricky one. H plus and hydroxide, H plus has no electrons. And so that's what makes it special. Because it has no electrons, then that entire bond is coming from our hydroxide one. Now, hydroxide is a coordination, or hydroxide is providing all of those electrons to form that bond. And so this is going to be an example of a coordination covalent because all of the electrons come from just one side. And so this is what we have when we have kind of water coming together. And that's because when we form that H2O, that difference between our hydrogen and our oxygen isn't enough for it to be a ionic bond. And so that's what's the difference there. This is different from something like Na plus and Cl minus, because when those come together and form that new bond, the difference between sodium and chlorine is still large enough to be ionic. And so that's what makes this an ionic compound, even though that bond is in some ways coming from the chlorine. The difference is when we look at the molecule that they form, right? So H plus and OH minus makes H2O, and that molecule is still covalent. And so this is a coordination covalent. All right. We're going to come back to this one in a second. Instead, I want to go ahead and finish off our Lewis structures. So let's look at carbon disulfide. So carbon disulfide, we should have 4 electrons from our carbon plus 2 sulfurs, and each sulfur is 6. So that gives us a total of 16 valence electrons. Now our carbon is going to be our center one. And I know it's carbon because it's farthest to the left. Then we have our sulfur and our sulfur. So that leaves us with 12 valence electrons left over. So we have our bond skeleton. Remember, I'm going to start from the outside and work my way in. So I want to start with the most electronegative atom. And so in this case, it's going to be my sulfur. But if we had sulfur and oxygen, right, something like this, then I would want to start with my oxygen. So we've done our sulfurs. Now those sulfurs did use up all 12 of my valence electrons, so I have none left. And so that makes me a little worried. My carbon here doesn't have enough electrons. So what I want to be thinking about is taking some of these electrons and moving them over to form a double bond. So I'll form one double bond there. Still doesn't satisfy my carbon. So I can go ahead and take another set. And so I'm going to take it from the opposite side. Remember that if there isn't a preference from one over the other, then try to split up your who you're taking your electrons from, right? 2 double bonds is more stable than 1 single bond and 1 triple bond. Now, if this was once again our carbon and our oxygen, I would actually form that triple bond with that sulfur first, because it might prefer to be with that sulfur over that oxygen. But then I would have to look at my formal charges to really kind of evaluate that. So now that we have our sulfurs, I'm just going to go ahead and make these look nice. Everyone's got an octet. I should check my formal charges. So carbon has 4 valence electrons. It's got no lone pairs. And it's got 8 bonding electrons. So it should be formal charge is 0. My sulfur normally has 6 valence electrons. It's got 4 unbonded electrons. It's got 4 bonding electrons. And so that also gives it 0. So now my Lewis structure has no formal charge. exactly what we're looking for. We're going to jump over and we're going to draw another one. So we're looking at SF4. So SF4 is 6 valence electrons plus 4 fluorines, and each one is 7. So that gives me a total of 34 valence electrons. Sulfur is going to be in the middle. Fluorine, 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 fluorine. We're going to start from the outside and work our way in. Oh, sorry, I should update this. So I used up 8 of those, making my structure. We have 26 left over. So that used up another 24. So we have 2 valence electrons left over. And now we're trying to think about where we would put those. So the tricky part is that everyone's got a complete octet, but we still have 2 electrons left over that we have to put in there. So we need to figure out who can hold them. So there's kind of 2 approaches that you can do at this point. One is you can look and see who can have an expanded octet. Between sulfur and fluorine, only one of those can have an expanded octet, and that's going to be our sulfur. Our fluorine isn't in period 3 or below. Another way that you can do it is to look for your FOMO charges. So sulfur, 6 minus 0, because it's got no lone pairs on it, 1/2 of 8. So it's got a +2. All of our fluorines are 7 minus 6 unbonded electrons, 1/2 of 2 bonding electrons, and they're all at 0. And so when we look at that, we can see who is still missing electrons, and that's going to be our sulfur. So we can add them in there. So when you're not sure what to do, one thing to start with is just to go ahead and find your FOMO charges, and you can use that to kind of guide you onto that next path. Okay. So our next thing that we're going to jump into, sorry, I'm trying to find the problem that I was looking for. There we go, is this one. When we think about our bonding, right, we have a couple of different kinds of bonds. We have ionic, we have covalent, and then we have metallic. And so NaCl, it's asking us when will it be electrically conducting. So NaCl is an ionic compound. And we know that because the electronegativity difference between sodium and chlorine, sodium is 0.9, chlorine is 3.0. So it gives us a difference of 2.1. Now, because it's an ionic compound, then we want to think about when will it conduct electricity. So electricity is electrons moving. And so that's going to happen if we're a metal because of the type of metallic bonds it has, or it's going to happen for an ionic compound when our ions can move. So our ions can move when it's aqueous because it's dissolved in that water. So we have an Na plus and a Cl minus, and now they can move independently of each other because they've separated inside of that water. Or when they're in the liquid state. When they're in the liquid state, we can also conduct electricity then as well. And so that's because when it's a liquid, those ions are now free to move independently of each other. But when it's not going to conduct electricity as a solid, it's not going to conduct electricity as a solid because those ions are now locked and fixed into one place. So let's go ahead and practice classifying them as ionic or covalent compounds. So all of them only have one type of bond. So you want to find out what it is. So in this case, this is C to H, K to F, C to O, Si to Cl, Ba to chlorine. And then you're looking at those electronegativity differences. So C to H is 2.5 minus 2.1. K to F, well, potassium is 0.8, F is 4.0. C to O, carbon is going to be 2.5, oxygen is going to be 3.5. Now for your exams, I will be providing those electronegativity values. So when you guys are doing these polar and nonpolar or ionic bonds, you won't need to use a periodic table. I'll either provide it as an electronegativity chart there, or I will give it for that specific question. Silicon is 1.8 and Cl is 3.0. And barium chloride is 3.0 for the chloride, and barium is going to be our 0.9. And so now we can start to classify them. So 0.4, that's that cutoff. And so if we wanted to get really picky, that's our nonpolar covalent. So that's going to make it a covalent compound. 3.2, well, that's enough for it to be an ionic bond. And so that's going to make it an ionic compound. 1.0, that's polar covalent, making it a covalent compound. 1.2, still polar covalent. 2.1, well, now that's going to become an ionic compound. And so you can see here that we get a little bit of variety. And we get some variety because of those electronegativity differences. So our metal and non-metal philosophy that we used to use for our ionic compounds, it's a good starting point. But now we can get a little bit more information by going a little bit deeper and calculating those electronegativity differences. And so if we have that information, then we want to be doing that, because that's going to help us get our most precise and most accurate results. Okay. Now, these next ones are going to focus on our enthalpy changes that happen for a process. And so we really want to think about what it means for our formation. So enthalpy of formation is when we take a material and we start it off in its elemental form. We make 1 mole of that product. Right? So this is the enthalpy of formation reaction. Or sorry, this is the formation reaction for CH4. And so we're looking for that delta H change. Now, to do that, we have to kind of come up with the pathway for it. And so they're giving us this extra piece of information that C to H bond, it has the average value of 414 kilojoules per mole. So every time we make a C to H bond, it requires, or it releases that much energy. Now that's going to be defined as us taking them from their gaseous atoms, so a carbon as a gas, plus a hydrogen as a gas, and turning that into a C to H bond as a gas. So this delta H is going to be 414 kilojoules per mole. And because we're forming it, then it's actually going to be a negative 414 because it's going to release that. So we want to start to piece together our process until we get something that looks like our reaction that we're going for. So what I want to do is I want to take that carbon and that hydrogen gas, and I'm trying to turn that into CH4. Well, I know CH4 is 4 bonds of a carbon to hydrogen. So if I have 4 if I have 1 carbon, 1 second. There we go. So if I have 1 carbon in its gaseous form and I have 4 hydrogens in their gaseous form, I can form that process, or I can form those 4 bonds. So what I want to do is I want to try to get them from my carbon being a solid to carbon being a gas. So I can do that with the delta H of formation. or sorry, not delta H formation, but the delta H of that reaction of carbon solid to carbon gas, which we have here as being 716 kilojoules per mole. And then I can take that and I can transition my H2 to 4 H's as a gas. And then once I have all of those, so now I have a carbon as a gas and 4 hydrogens as a gas, I can now make my bond, right? So we kind of have those different steps going on. So we're kind of taking one thing, converting it into another through those steps. So let's think about that. When I transitioned from that carbon solid to my carbon as a gas, we're going in the same direction as this. And so we're putting in 716 kilojoules. So my delta H1 is going to be 716 kilojoules per mole. And that's the amount of energy it takes for us to take that carbon as a solid and turn it into carbon as a gas. From there, we're taking that hydrogen, we're turning it into hydrogen as a gas. So that's my 872.8. And then I'm going to do that carbon to hydrogen bond, but I'm going to do it 4 times. So I'm going to add to this my 4 carbon to hydrogen bonds, and each one of those is negative 414 kilojoules per mole. And so when we add those up, we can get the enthalpy change for this. So 716 plus 872.8 plus 4 times negative 414. And so we get a delta H of our reaction of negative 67.2 kilojoules per mole. And that's going to be the delta H for the reaction of that process. Okay. We're going to stop there for now. I'm going to come back and we're going to try this one as well. So this is going to be in the next video. So I want you to use what we just did with the average bond enthalpy and go ahead and give it a shot for this one as well.